Morning, everyone. Welcome to this day of the SPM&SMI conference. My name is Charlie, the General Chair of the conference. And it's my great pleasure to host the second keynote of the conference. Give it to a talk from Professor Bernd Bickel. I know Bernd Bickel for many years, but this we have memories the last met person is around 10 years ago. Okay, this is some of the gems like during the a lot of things like this. It's like pandemic, it's like many of the chances of growing persons stuff like that. And Bird has a fantastic and he's currently a professor of computational design at ETH, and he's also a research scientist at Google. And he previously served as the professor and vice president at like an ISTA at 2020, it's like Institute of Technology. Right. Okay. And worked as a research scientist at Disney Research. And he received his PhD in computer science from ETH Zurich 2010. His research uses kind of an intersect of multiple areas, including visual computing, digital fabrication, machine learning, and focusing on computational tools that bridge the digital design and physical manufacturing. That's why we know each other very well. Okay. And his work includes the high-fidelity construction and data-driven material modeling, functional metamaterials, creative AI, and generative design, integrating physics-based solutions, machine learning to create high-performance tools and systems. And Bernd's contribution have been recognized with the technical achievement award from the Academy of Motion Capture Arts and Science, and SIGGRAPH significant new research award 2017, and the ERC Starting Grant is 2016, and the ETH Medal is like 2011 is doctoral dissertation. Okay, thanks and welcome, Bernd, to come to the stage and give us that.
Yeah, thank you so much. Thank you so much for the kind introduction. Yeah, it's a true privilege to be here. Really amazing and beautiful. Okay, perfect. All right. So yes, thanks again for the very kind introduction. Also, big thanks to all the organizers. Fantastic to be here, and yeah, it's a really beautiful city. So in my talk, I want to explore the transformation of design workflows from traditional CAD towards intelligent design systems. And I think in general, computational design is a very exciting topic because basically design is everywhere. It is in everything that we need to create. It's in buildings, in the built environment, in everything that engineering creates, in material structures, and even in computer science in the form of data structures, neural network architectures, and programming languages. And now, I think it's fair to say that in all of these areas, actually finding excellent designs is extremely challenging because we're facing very complex problems that go actually also beyond pure performance. So they also include factors such as, for example, environmental sustainability, cost effectiveness, and also communication challenges between stakeholders that need to work together to actually, solve a complex problem, just to name a few. So I think across all these application areas, there is one very central challenge, and that is how can we more efficiently do design? How can actually machines create complex designs? And how can machines actually work together with humans to create designs? And what are the key problems actually such that machines and humans are actually successful in finding good designs? Now, I think this topic is extremely timely. So we are all witnessing this omnipresent rise of technology across all fields. And in particular, we see this exponential acceleration of AI. which comes with really disruptive possibilities for analyzing vast amount of data, and also the generative capabilities when it comes to images, text, or code, are truly stunning. On the other hand, in particular, when it comes to solving difficult, for example, difficult to define problems, the human has very unique skills when it comes to creativity, empathizing with each other, also framing the problem, and also ethical decision making. And then on top of that, that's also my role actually at Google. I'm in the XR team. So there are also new spatial compute platforms on the verge, for example, augmented reality. So there you can, for example, imagine a device that can actually sense the environment, basically see what you see, hear what you hear, and also have a display that allows you to seamlessly blend between virtual and the real world. And this together, I think, really provides exciting possibilities of bridging humans, AI, and their surrounding, and thereby unlocking new workflows. Now, a large part of our research is actually motivated by the belief that there is actually an urgent need to harness the potential of this technology while also preserving the human creative process and basically ultimately empower humans, so basically giving humans superpowers to do design. Now, to get there, we're facing many interesting technical challenges, and one very central challenge, in my opinion, is this question and challenge around control. So what I mean by control is actually that an engineer, an artist, or designer can very accurately specify what they want to model. And this challenge is, of course, also tightly coupled to computer graphics, to our community, which is very much centered around 3D modeling and tools to actually create content. And if you think about the last 50 years of research, the history of computer graphics basically is first came control and then quality. So it actually took decades to establish the right abstractions, so curves, triangles, polygons, meshes that would allow us to draw exactly what we want on screen. And while they got complemented recently by some volumetric representations such as 3D Gaussians, in general, these fundamental building blocks haven't changed much over the last decade because I think they proved to be the right ones. But what's dramatically different is the visual quality. So here we actually saw big changes going, for example, towards real-time photorealistic rendering. So to summarize, in classical CG, basically we first define exactly what we want to draw, and then it gets drawn. Now, if you look at today's AI capabilities, this actually have completely inverted this progression. So today's generative models is actually achieve photorealistic rendering quality, basically in some sense replacing that entire traditional graphics stack through massive scale training. So with a simple prompt, one can generate really stunning photorealistic images. So what you see here is actually a result for a design study for a facade, actually from an architecture student from a course that I'm teaching at ETH. And yeah, so basically generative AI models, they aim to learn this underlying probability distribution of data they're trained on, and allowing you to actually generate new samples that actually resemble the structure in the trained data. And comparing it with classical graphics, basically the deterministic nature of the graphics pipeline has been replaced by probabilistic models. Now, on the one hand, this is really amazing because now everybody of us can, in just a few seconds, generate photorealistic content, something that is very, very difficult to do with a traditional approach. But as the downside, actually, we lack precise control that actually decades of CG research have provided. So we cannot easily adjust the geometry or materials or manipulate light with the granularity that, for example, a good designer would expect. So in terms of granularity of control, there's a really huge gap between what traditional graphics technique and Gen AI can do. And one very obvious, but also I think very relevant question is, in my opinion, how can we actually close this gap? So how can we work towards systems that can provide us basically the best of both worlds? On the one hand, intuitive high-level prompts, for example, as provided by text-to-image AI models, but also benefiting from precise control of traditional graphics representations. my group tries to tackle this and also other challenges by basically trying to find solutions that are grounded in geometry processing, physics-based simulation, and then also somehow combining it with insights from machine learning and programming languages. And just to give you a very brief overview of what we did. So in the past, we focused actually quite a bit on human modeling and perception, and more recently now started shifting our focus to XR and scene perception, as well as also using or utilizing large language models for design. And yeah, a major focus is computational design tools with very broad range of applications. So for example, we've been working on material representations, designing architected materials, speeding up simulation and optimization approaches to enable interactive design. And we also try to gain a deeper theoretical understanding in design spaces. Yeah, finally, we're also very much interested in actually applying design for construction and manufacturing purposes. For example, designing molds for injection molding and casting, or designing new closed loop controllers for material deposition strategies, for example, for 3D printing. Yeah, now actually, as promised, as part of this talk, I want to explore this transformation of design workflows from traditional CAD tools towards learning-based design systems, and try to illustrate this with multiple examples. And my intention is actually to focus a bit on the navigation aspect, so basically categorizing how designers move through design spaces. So we'll actually start by presenting a general simulation-based approach for optimizing CAD data, where we basically move along gradients of explicit constraints. And then we will look at some more interactive approaches, which will allow to keep the designer in the loop and yeah, interactively allow the exploration and also optimization of designs based on, for example, some trade-offs. And there, surrogate models actually allow to predict, for example, complex material behavior, such as bending behavior, for example, of wood or glass in real time. And then towards the end, we will look a bit towards AI and more data-driven approaches, actually navigating some learned latent spaces, touching both briefly on diffusion and vision language models. And yeah, and then I conclude by trying to speculate a little bit about the future. All right, so with this, let's get started with this simulation-based approach. And yeah, basically, I think an important aspect or important practical step so that humans and machines can actually efficiently do co-design is actually to have optimization methods that can work on parametric surfaces. So basically, and this is the community here, basically all popular CAD tools, they work with parametric surfaces. They are the representation of choice for many engineering applications, also construction, robotics, architecture. And yeah, this idea of using such mathematical parametric surfaces is quite old, right? It goes back to the 50s and 60s, but it's still the method of choice in CAD, as it allows to mathematically very precisely define surfaces with, for example, smoothness guarantees, for example, perfectly rounded off edges or holes with very easy and intuitive to control parameters. Now, this is great, but now if someone wants to actually test the design and simulation, the typical workflow is usually that you start with a parametric CAD model, as you see on the left, but then you somehow have to mesh it. Then you run a simulation on the mesh domain, for example, run a finite element simulation to test occurring stresses, just to give you an example. And then for optimizing the model, of course, the CAD model needs to be updated based on the analysis. So we actually we want to know now, how does our analysis, the physical performance of the part, change with respect to small changes of the parameters of the model? And for this, ideally, we want this process to be smoothly differentiable. And one challenge is that at least if you do it naively, this is not the case here. So the problem is basically with each update, for example, by enlarging the hole in this example, we need to create a new simulation mesh. And as you know, meshing itself is non-trivial. And even if it's successful, the problem is that the mesh combinatorics change. So this can actually create some noise in the simulation which can, for example, have challenges then with having this being smoothly differentiable. So, in our work, in one of the papers, we try to address this problem by actually creating a pipeline that allows to easily optimize CAD models automatically. So the idea is that we start with the CAD model as input, then parameterize it, so basically telling the simulation which high-level parameters can be changed. And then at the core of the system, which is also the main contribution of the work, is basically analysis based on XFEM, which is fully differentiable and allows fully automatic optimization of models based on some desired objectives. And as output, we get actually an optimized CAD model, which can then be further used, for example, in an existing CAD workflow. Now, as I mentioned, the approach is based on the XFEM method. So this is an extension of the classical finite element method with the advantage that the boundary of the object we want to simulate doesn't need to exactly match with the underlying simulation mesh. So for example, we can use a regular simulation grid and embed the object in there. So for example, when looking in one of these elements, parts of the objects can be inside and parts outside, which is fine. So there is no headache about meshing that needs to conform to boundaries. Now, fortunately, as always in life, there is no free lunch. So even we have that, we still actually need to be able to accurately integrate certain quantities over the object's volume to run the simulation. And this, in the first step, might look like a challenging problem. For example, when looking at this cooling unit, because we require a method to integrate over all the subvolumes and over the regions of the model surface. And I mean, typically, numerical analysis, one would use a quadrature rule, which means basically approximating this a definite integral of a function with a weighted sum of function values at specified points, where the weights would be pre-computed. But in our setting, we cannot pre-compute the weights because we want to update the model. So the model itself is actually changing all the time. However, the good news is, that there is actually, in the paper, actually, I will not go into details, but we discovered a method for doing this precisely, efficiently, robustly, which actually, as a result, allows us to achieve a good precision and then basically be able to use the XFEM method in a differentiable way and running optimization on CAD data. So as I said, because of time reasons, I will not go into details. But if you're interested in check out the paper, or we can talk during the break about it. Now, trust me, assuming now we can run the simulation in a robust way, an efficient way. What I want to focus a bit more is actually now for performing the optimization. It's actually important to be able to specify what should be optimized. And yeah, this is a bit what I want to focus on here. So a good parameterization should provide sufficient degrees of freedom to enable meaningful improvements of combinations of objectives while actually preserving the underlying design intent of the CAD model. And on a low level, we represent the CAD model, for example, as NURBS patches, and their control points are denoted here as Q. And it would actually be a bad idea to directly start manipulating these nodes, because if you start moving them around, right, you basically lose the design intent of the model. So what we rather want to do is we want to allow the user to describe some intuitive high-level parameters, such as, for example, the radius or center of a hole. And then, of course, these high-level parameters, here denoted as P. From those, you can then compute the control points Q. And by only modifying these low-level parameters indirectly through P, primitives actually retain their shape. However, in addition to that, you also need additional constraints to preserve the design intent of the CAD model. And just to give you one example, is this fillet here, which you can see in the middle, which is an initially sharp edge that has been rounded off by adding a cylinder segment. And this cylinder is actually tangent to the planes of this cube. And if this tangency is not preserved, then actually, sharp edges could occur, and you actually start breaking the model. So to solve this, actually, once a CAD model is loaded, what we do is we actually traverse all pairs of adjacent surfaces and detect tangency relationships that need to be preserved. And this is done automatically by basically using a lookup table that stores possible relationships between primitive types. And whenever a situation like this is encountered, actually a list of implicit constraints is generated for the pair of surfaces in question. And then, this yields nonlinear constraints that basically need to be retained during the optimization. And also on top of this, we have a UI which actually allows the user to define some high-level model parameters, for example, also keeping certain surfaces fixed, or to enforce, for example, symmetries in the model. And now with this, that we actually have this robust underlying XFM method, we can actually now run quite nice optimizations. And I want to show you some results. For example, starting with this simple wrench. So this model here is composed of a set of NURBS patches that are subject to many tangency relationships along its each edges, which you see on the right-hand side. And the parameters here are the slot, the hole, and the fillet radii. And you can now see how it's first modeling in the CAD tool, then optimized with our framework. And then after that, you can actually see you can even go back to the CAD tool and keep changing things. Here's another example of an asymmetric wheel rim. So here the goal is to optimize several objectives at the same time. So the center of mass and the inertial axis so that it can spin stably. And we also optimize at the same time the strength to weight ratio under axle load. And you can just basically run this optimization, and you can also 3D print it and test it. And here you can actually see the comparison, and the performs much better. Here's another actually quite a simple example. So this is a fidget spinner. So here we only looked at the mass properties, and we actually have 10 parameters to control the shape and the size of these handle holes. And as you can see with the real life demonstration, actually, does its job. Now, I want to move on a bit. So, while this is a very general framework that removes some of the headache around meshing, of course, several important aspects, such as, for example, how to handle topology changes or material interfaces are currently missing and also require more research. But of course, also another challenge is speed. And actually, how can we speed up the optimization? And I mean, adaptive refinement would be one obvious choice, but for much more efficient algorithms that basically really support interactive form finding, one would, I guess, need to change the strategy. And in the following, I want to focus on how to achieve interactivity by basically trading some of this generality with more specialized tools or more specialized focus. And I want to first focus actually on structures that are made of active band elements. So active banding allows the realization of really intriguing structures, and has actually also very long history, playing a really important role in construction, with very early examples, for example, from turkmentents. And I think it's fair to claim that this aesthetics from banding and band element, still fascinates designers, architects, but also mathematicians, because there's a lot of also interesting, underlying geometry in it. And a specific example from construction is, for example, this really beautiful pavilion from Achim Menges and Jan Knippers from the University of Stuttgart. Or also you can see it actually in bent glass used for modern buildings. For example, this Opus Dubai building by Zaha Hadid architects. And personally, I find this topic also exciting because it presents a very economic way of realizing intriguing shapes, actually from flat panels, which are easy to make, easy to transport, yeah, and also pose interesting opportunities and challenges for deployment. So motivated by this, we started exploring how to design flat, flexible panels with some tailored mechanical properties that, when assembled, actually resemble a smooth shape. And in this example shown here, we actually developed a design system that actually tailors the mechanical properties of these spiral-like shapes, such that when you basically fold it together, you get your desired 3D target shape. And yeah, this system actually triggered quite some interest. And then actually with two partners, one from the University of Pisa, actually under the lead of Paolo Signoni, that many of you might know, and the other one is actually the School of Architecture at the University of Technology in Sydney, actually under the lead of Nico Pietroni, which also many might know. Ah, he's here actually. Oh, fantastic. Hi, Nico. We first of all, I mean, we worked together on already this system I showed before, and then they employed the system and also extended it to actually explore the design of innovative lightweight structures, such as, for example, this pavilion here. And the workflow basically starts from a parametric surface from which we analyze the curvature and place a cross field. And then basically a quad mesh is computed, and the software then automatically splits them into patches in sizes that are manufacturable. And basically here each quad contains a spiral shaped material element. And to ensure actually that this pavilion takes the desired shape in equilibrium, our software, what it does is actually tunes this parametric spiral-like shape. So this is actually under the hood. There is a differentiable data-driven model trained actually from offline FEM simulations, and it can actually predict all forces when the spiral is stretched, bent, or twisted. And yeah, then once such a configuration is found, so basically you can give it a target shape. It tries to optimize the spirals. If you find one that works, structure can be very easily manufactured. So here with milling. Nice thing is it also fits conveniently into boxes for shipping and can be assembled on site, as you can see here. So these are actually Paolo Signoni's students from CNR that are assembling the structure. Actually also a nice success by Paolo and also Nico. That this was actually shown at the International Architecture Exhibition, the Biennale in Venice. And here you can actually see how it's assembled. Yeah, here you see it fully assembled. Now, moving a step further, active bending can also be an appealing method. I mentioned this already a bit before, when used with glass. So in this project, which was actually a collaboration with Helmut Poppmann, our motivation was to actually enable a new technology for designing glass facades that can be manufactured in an economic way, which is actually cold bending of glass. So cold bending of glass is a relatively recent method to achieve doubly curved shapes with glass panels. And it's based on the fact that actually glass can safely withstand certain mechanical deformation. So the idea is actually starting with an initially flat glass panel. We can bend it elastically to basically a pre-manufactured curved frame. And yeah, this method is much cheaper than traditional hot bending of glass, where basically glass is heated up and brought into shape. Because there, I mean, you need to shape each panel individually. As usually, if you have such intriguing facades, none of the panels are exactly the same. Now, however, of course, also working with glass comes with some challenges. I mean, glass is brittle. And so, so therefore, basically, this the shapes that you can achieve with cold bending, it's non-trivially constrained. And yeah, basically our aim was to come up with an interactive design tool that is suited for this fabrication method. Basically allows designers to quickly explore which panels can be achieved with code bending and which cannot. Show you this quickly first, the result. So yeah, our system basically allows to interactively explore these facade shapes, and it color codes which shapes require a hot glass building, so basically which cannot be cold bent, and which ones are fine to be manufactured with cold bending. And so architects actually get immediately feedback on the shape and also the stresses of the individual panels. So the prediction time for this is approximately 0.1 seconds for 1,000 panels, which allows now to truly interactively explore shapes and try to find shapes that are visually appealing. Now, these interactive rates, they're achieved basically because we trained a relatively simple predictor. So the model architecture is actually a mixed density network. The input is a panel boundary, and as an output, which might be a bit surprising, we do have two Gaussian distributions. And each of these Gaussian distributions, the mean contains actually the interior control points, which is the shape of the bent glass, or defines the shape of the bent glass, and the maximal stress of the panel. And we do have two shapes as output, because for a specific frame, one could actually have multiple stable states, which can look quite different. So therefore, yeah, I think it's actually really important to try to learn to predict both of these and not just one. And yeah, the probabilities here, they sort of reflect the likeliness of the shape. And what we do is basically we train this model on almost 2 million simulated panels. And if you would basically run these simulations on a regular PC, it probably would take multiple years. Yeah, and what I want to mention here is during the training process, we actually made two very interesting observations that actually, I would say, go beyond of just using a model to make things faster. So first, we realized during experiments that the network allows us to discover stable states that were initially not in the training set. So then basically what we do is we simulate these newly detected states to actually verify the observation, this is truly a valid state. And if so, we add it back to the training database, thereby basically iteratively improving the results. And I would say second, being able to predict not just one, but multiple stable states is actually a big advantage compared to a pure simulation-based approach, where it would actually, I would say, be fairly easy to basically identify one local minima of the deformation energy, but it's hard to reliably find both. Yeah, so I think here the advantage goes beyond just being faster. Now, I mean, this is also differentiable, so it also, because of this, supports quite straightforward shape optimization. And here is just one result I want to show you briefly. So by optimizing the design for fabricability, for example, by slightly adjusting the shape, in this specific example, one can drop the number of breaking panels, or basically panels that would be needed to be made from hot bending, from 1,500 to 900, while actually still staying, I would say, I'm not sure if the designer agrees, but staying reasonably close to the initial shape. And yeah, this results to this example, approximately 40% reduction of the number of panels that would otherwise needed to be hot bent, and therefore allows for much more economic fabrication. I'll also not go into detail here, but you can also optimize for example, the angles of how two panels meet, so that you have like nicer reflections. And yeah, you can see an example of this previous building that I've shown you. Okay, now with this, I want to switch gears a bit. So we have looked so far at designing with very specific material structures, for example, spirals. And I want to zoom out a bit and start looking at metamaterials a bit more broadly. So as you probably know, metamaterials are a very large topic of interest in science and in engineering. These are actually materials where its properties arise basically from this carefully designed structure of the material rather than its chemical composition. And in many domains, engineers are actually constantly searching for materials with novel, desirable property combinations. For example, I'm talking a bit from the architecture and construction perspective. This is relevant, for example, for designing very lightweight materials that are also stiff. They reduce the amount of material needed, for example, for building an object, or also reducing the fuel required for transport because it's more lightweight. Or a topic I'm very starting to become very interested in is tuning actually thermal conductivity. This could improve, the micro climate shaping capabilities of materials, leading to more sustainable but also more enjoyable spaces. Or also acoustic applications, for example, preventing certain frequency ranges from being transmitted through materials. Now, these applications are all very exciting, but they basically rely on our ability to effectively now discover and design a wide range of metamaterial shapes. And this problem has been very widely studied. So there's a lot of related work on this, for example, including approaches to geometrically explore and enumerate topologies. There's also many optimization approaches, including topology optimization. But I would say basically they all either struggle either with a limited diversity of structures, or they face challenging nonlinear optimization problems, right? As soon as your objective, of course, becomes very nonlinear, it's difficult to optimize for structures. So we started exploring a bit if a data-driven approach could address this problem. And in particular, we tried to leverage a diffusion model to actually learn a latent diffusion model that can, basically guided by desired properties as input, synthesize the corresponding microstructure. And it turned out, and this one lesson I want to show you briefly, that we ran into, if you try to do this naively, it's actually quite tricky to do. It did not work in the beginning. So basically what we did was we started by encoding the geometry with an autoencoder, and then visualized the latent space with color coding, actually the Young's modulus here, so the elasticity of the sample. And as you can see, this looks here very, very noisy. So which basically means that structures that are very close together in latent space could actually have very different mechanical properties. And this makes it challenging to learn the relationship between property and geometry. So, one trick to overcome this, what worked well for us, is actually to incorporate some physical priors during the training of the autoencoder, enabling the model to basically jointly capture both the geometric and also the physical details. So here actually the idea is quite simple. So we basically encode the geometry as signed distance fields in planes that also provide and guarantee symmetry. And in addition, we also encode some displacement fields of the microstructure. So these displacement fields actually result from deformations under standard force tests. So they basically, in some sense, they encode the physical behavior. And by the way, also from those, we can quickly compute the homogenized mechanical properties of the microstructure. And if you use these together, turns actually out you get a much better latent space, where now both similar geometry and similar behavior are basically grouped together. I think this is now also quite nicely visible in this plot here. And to see how well this works, we can now actually look at interpolation in this latent space. So here you can see actually two start models, which are truss structures with low Young's moduli and small volume fractions. And at the end, you see models that are plate structures, which have a high Young's moduli and actually large volume fractions. And then basically we just interpolated in latent space. And you can see here, I would say the interpolation works actually quite nicely. So these models retain initially their trust topology, then increasing the volume fraction to achieve higher Young's modulus values, and then gradually they transition into these plate configurations. And we also plotted the path actually in material property space, which I think looks quite reasonable. And you can now, for example, use this to quickly synthesize optimal stiffness weight parts. So here you see a pillow bracket for which we actually ran a coarse optimization for finding the optimal material properties. And then basically from these, the actual material structure is the microstructures are generated on the fly and the model is printed. Yeah, now basically, this is nice, but of course, to get to a latent model from microstructures, you require a database of training samples that do cover a wide range of available microstructures. And now, unfortunately, getting such a database is tricky. We cannot just scrape millions of samples from the web as you can maybe do with text or images. So we somehow need to bootstrap the process by modeling them. And yeah, and I think this is not such a simple problem. So imagine, for example, you have to model all these microstructures shown here in your favorite modeling software. So basically, you would need to start composing elements such as struts, shells, and solids in a way to achieve interesting physical behavior. And yeah, this is hard to do. And actually, I have seen many students actually also in the, for example, material engineering side that actually really iterate months long over this. So we actually thought, an interesting central question is, what is actually a good representation for modeling this wide range of structures? And can we actually come up with a representation that allows us to efficiently design this wide range of structures in a more unified manner? So to address this problem, we came up with a procedural approach. The idea is basically, we came up with a graph-based representation and combined this with a new user-friendly interface that actually allows researchers to quickly model cellular metamaterial structures. And basically, what it allows you to do is it allows you to build metamaterials by composing various building blocks in a quick way together. So at a high level, basically, our approach uses a set of operation nodes to first define small skeletal pieces of the target structure, then apply a series of transformations like mirroring or rotations to basically fill the unit cell, and then apply thickening or other geometry processing operations to finally generate a physically realizable structure. Now, basically, conceptually, you can think of this as small compute graphs or programs with instructions that allow you to compute a wide variety of microstructures. And yeah, basically, I would say that the secret sauce behind this is to actually provide the right building blocks and geometric compute mechanisms to cover a wide range of structures, as you can see in a second. So here you actually see a few examples. So first, building a shell-like structure, then a shell plus a truss structure. Here we see a truss structure. And then also, you can also use this to actually create minimal surfaces. For example, you can see in a second, this Schwarz P. Schwarz D. Or the gyroid. And yeah, I think this is in particular nice about the system, that you have this ability to actually create a wide range of such minimal surfaces, in particular these TPMS structures. TPMS stands for triply periodic minimal surfaces. So they're basically independent, periodic in three different directions, so you can easily tile them and also they have these properties of having minimal surfaces, and this is exciting because uh, these or some of these are actually considered as the most promising metamaterial structures. So, for example, TPMS, they have amazing trade-offs between stiffness and density, so they can approach some of the theoretical upper limits. And they're also ideal actually for additive manufacturing because they're self-supporting structures. And yeah, for example, by now unlocking these variations of these TPMS structures, we can now do much more thorough exploration of these promising structures. For example, you could easily generate structures and examine properties of weight versus stiffness trade-offs, designing anisotropic elasticity, or also we explored this for designing structures with phononic band gaps, so basically acoustic sound blocking abilities. Now, again, I want to take a step back. So basically, now with these, in some sense, we have unlocked precise control, but actually now creating them from scratch can still be labor intensive and does require expertise. So I think an obvious question is, can AI help us actually to generate these procedural materials? And I think in general, actually, this could be extremely useful because the concept of designing materials in procedural form is not just for metamaterials, but actually it's widespread in many other areas as well. I mean, as you might know, right? I mean, it's like used for landscapes, plants, buildings, in urban design. And one particular case I want to look at together with you is actually the application in visual effects, where procedural material graphs are widely used for actually appearance design. So there, basically, they allow you to model and describe how a material, such as, for example, marble or wood, looks like, what texture it has, and also how it reflects and interacts with light. And these are basically node-based, so meaning you can actually control every aspect of this texture, such as color, roughness, reflections, and bumps procedurally. It is really, really cool, and if you have a good artist, I mean, they can create incredible materials with this system. So you can have, things that look mossy or rusty. And then one nice thing is, of course, you can apply this to an arbitrary 3D shape and texture, basically 3D scenes. However, as you can see here, these material graphs can become quite large and complex. So this is the graph for this rock-like material here. And yeah, you need to be a really good artist, right? That you're able to actually design something that then looks exactly as how you want it. So therefore, we started to investigate if we can actually generate these graphs from pictures or text descriptions instead of creating them manually. And in the beginning, we just tried naively. Maybe we can just ask a vision language model to do that job for us. So we tried this. So basically, we gave an image, and then we prompted a model and basically asked, please create a Blender procedural material using Blender's Python API to match the appearance of the image when rendered on a flat surface. And we tried this, but unfortunately, this was the output we got. So you can see actually, this does not look the same at all. And I guess the very likely reason for this is this fails because these procedural material programs, they're very domain specific and very much underrepresented in the training data of this vision language model. So to solve this problem, basically we create a fine-tuned a VLM to actually predict procedural materials, and it basically takes input an image, then produces code and executes the code in Blender, then yields actually the shader node graph of the material, which is then rendered on an image, as you can see on the right-hand side. And once again, also what I mentioned before, I mean, if you want to now train such a model, you somehow you need data. And I would say this was the main challenge here. And yeah, and also, I mean, this challenge, you have it basically almost anywhere, right? Where you want to do something domain specific that you don't have enough data. So I think in general, yeah, an important question is how can we actually develop effective data augmentation strategies? Now here in this project, our strategy was to actually leverage the pre-trained vision language model to perform data augmentation. So basically, the idea is to take a random sample from the training database and then use the reasoning capabilities of the large language model to actually generate new programs from that example. And I guess the key here was, that we did not just do basically random perturbation on the graph, but actually in some sense, leverage the generalist knowledge of the vision language model that knows, for example, how Python program is structured, and therefore the likelihood of a reasonable program augmentation is much higher. And then you can actually, of course, check the validity and quality of the material. And if the material is of high quality, then you can actually, add that basically newly discovered material to the training database, and with this basically grow your database. And with this, we managed actually to go from only 800 materials that we had in the beginning to more than 500,000 samples. And yeah, with this, we were able to get the system running. Here you now see a couple of tests. So these are photographs of different materials as input. And here you can see actually the matched output. And the match is not absolutely perfect, but I think it's actually quite close and does resemble the structure of the material. Now, just want to show you two more projects very quickly. So far, basically, we have used these vision language models to generate material graphs. And now going one step further, one can ask, for example, can these vision language models also be useful for directly generating fabricable 3D models? And as a first use case here, one of the students I collaborated with, Kenji Tojo, he started looking at how to generate 3D wire art from a concept given as an image or words. So for example, from these input rows, we would love to actually get the 3D wire rows on the right-hand side that is also manufacturable. The challenge here is actually how to go actually from a very abstract concept to something that you really can build that also respects the necessary fabrication constraints. And also, the wire model is actually a very abstract representation of the input, so there is no one-to-one blueprint you can follow. So to just give you very quickly an intuition of how we solve this problem, actually we started with a random 3D curve, in this example here, with the text input shark. And now the key problem is actually that we need to know how similar is this 3D curve to a shark. And basically to answer this, we just use a vision language model, which can capture the semantic meaning of what is in an image. For example, how likely it is that you see a shark. And also, I mean, this model is differentiable. So we can actually now start changing this current 3D wire model iteratively so that it gradually starts looking more and more like a shark. And yeah, with this system, I can now show you briefly basically what the optimizer does. So you see basically starting from this random curve, it actually does converge towards a wire shark. And here are some more examples. So this is a multi-view wire art generated from text prompts that we actually also fabricated. So the input here were cat from one view, dog from another view, and bird from a third view. Now, yeah, I mean, of course, this is a more artistic application, but I'm excited about it because we're able to show a new way of basically using generative AI to create actual things by also solving I would say, a challenging design problem that involves both some perceptual constraints And we had this in there, via a vision language model and physical constraints. By the way, I did not talk much about the physical parts. Basically, there is also, simulated also checks certain constraints. For example, that the bending angles are not too high. There's also some checks that you, basically have a good chance of fabricating these models afterwards. And I mean, one nice thing is, I mean, of course, there was no custom trained ML model for wire art. So we just leveraged this very generic vision language model that understands the correlation of abstract concepts in images, and then we could actually extract the relevant information to design the 3D object. And I believe this concept is very generic and probably can be applied to many other application areas as well. In particular, I think for design and in architecture. Now, the very last thing that I want to show you before wrapping up, this is actually some very recent work that was just accepted to ECCV. Here we also went a step further and try to see if we can somehow also do something with video models. So probably all know, right? These vision models, these video diffusion models, they have advanced, like crazy over the last 2 years. And I guess we're all, stunned when we saw, for example, these videos from OpenAI, what Sora can provide in terms of temporal consistency. So basically, based on this, we asked the question, can we maybe, and I work a lot with architects, can we use them to basically simulate urban wind flow? And we thought actually maybe the problem is sort of similar. So basically we have a similar framing. So basically there's a projection onto the horizontal plane. There's basically a velocity field, and that evolves basically as a frame, as a sequence. And the idea was basically, so we start with a pre-trained transformer-based latent diffusion model, and then basically want to apply it to wind fields. Now, if you just do this directly, right, it doesn't work because there's a pretty big domain gap between what you would like to see and what the video model was trained on. But actually, it turned out that you can actually quite easily fine tune this general video model, and with actually quite reasonable amount of data, because it also, in some sense, it already has an understanding of how things move, and then apply this to these wind fields. And what we basically did was two things. One was we fine-tune the decoder weights in this encoder-decoder structure. So we have a data set of 13,000 simulations, and we also had added some physical loss prior to basically have a divergence penalty to enforcing incompressibility, and also making sure if you have a building layout that basically, things don't flow into buildings. And this gave us much better also reconstruction quality. And then also we've basically fine-tuned this diffusion model conditioned on the urban footprint and wind speed and domain size. And this then basically gave us a surrogate model for urban wind simulation, basically producing full velocity fields over more than 100 frames in under a second. And also if you use a differentiable rasterizer, you can also make this whole machinery completely end-to-end differentiable, and with this, for example, also start moving around or optimizing building layouts. And as I said, I mean, the main application we're interested in is in urban design. So it actually really matters, the layout of buildings, how it affects the wind speed through it. And you basically want to prevent two things. I mean, you want to prevent that the wind speed is too high, because it creates very unpleasant experiences. And I know, for example, I lived for a long time in Vienna. There are some parts in the city where because how the buildings are aligned, there's extremely high wind speeds. So you can even like, if it's very windy, yeah, you don't even want to go out on these streets. Whereas in other areas of the city, it's completely fine. And the other thing, what you also want to prevent is that, also that you don't have any wind speed. So basically, if things are too much locked in, then maybe pollutants, accumulate, or also that these areas get too hot. So basically, you want to find a good trade-off. And yeah, you can basically now just use this model to very quickly evaluate a certain layout. And as I said, because it's also differentiable, you can ask the system to maybe move around buildings to find a better trade-off of these objectives. With this, I want to wrap up. Sorry, I'm 5 minutes over time. Is that okay? Good. Yeah, I want to conclude. So just to, first of all, quickly summarize, yeah, I've shown you various flavors of design workflows, starting from traditional CAD tools, supporting optimization based on explicit constraints and PDs. And then we looked at some interactive approaches, which allow to keep the designer in the loop and interactively explore design trade-offs. And they are basically surrogate models allowed us to predict complex material behavior, such as, for example, the bending of wooden spirals or the shape and maximum stress of glass panels very quickly. And then we shifted focus and started exploring diffusion models and vision language models for tasks such as metamaterial design, procedural materials, and also these wire sculptures. And still, basically, with all of them, we had physics-based simulation as an additional ingredient. And with this, we managed to either increase the robustness or also ensure constructability in the real world. But also at the same time, we were benefiting basically from these, being able to, in some intuitive way, basically use text, for example, or image prompt to design the, to drive the design process. Now, again, taking a step back, basically when creating design systems, you're very often motivated by this goal, and actually started with this motivation that we want to become more efficient. And I would say, actually, looking back, we clearly have seen strong efficiency gains, and especially now, also in general, if you look at it, with the success of large language models and generative AI, the acceleration we see is really, really incredible. And what we also see in general is a very fundamental shift from basically how to do it to basically what we want to achieve. And I want to explain this a bit more in detail, particularly looking at software engineering. So I think this shift is probably most prominent at the moment in software engineering. So there basically this gap between traditional software engineering and AI-based coding, it has really widened a lot from being just a nice tool that makes you a little bit faster to a very fundamental shift in philosophy, where basically we moved from instruction-based development, so basically telling a computer how to do it, to an intent-based development, where basically we tell the computer what we want to achieve. And yeah, this allows entering really this area of massive expansion ratios. So basically a human, you can very easily write 50 words of text, and then the AI generates thousands and thousands of lines of code. Yeah, and now, as I said, I would say, and I also see this at Google and many other companies in software engineering, this really has fully arrived. And there are studies that basically now say, in terms of adoption, there's more than 90% of the developers in Fortune 100 companies are using AI-based intent tools, and also in terms of volume. So in now full stack environments, AI-generated code is estimated to account for now more than 50% of all new commits. And I'm just wondering now, what does this mean for architecture, engineering, and construction? So there, I mean, the adoption is slower, but it's of course also changing the industry. And I think an obvious question, in my opinion, is, is there anything we can learn from software engineering for computational design and the areas it's applied in, for example, architecture engineering and construction. And I think at the first glance, things maybe at a high level are not so different. So you can maybe think of CAD and BIM, so building information modeling. Um, these models, they can be viewed as some sense as some specialized programs, right? Or more accurately, parametric programs that define a build asset. And we can, of course, try to leverage and build on the developments in code generation. Now, and basically also with this, moving up the abstraction level. Now, basically, what does this mean for AC? So what I see in software engineering is actually that the focus starts a lot, from programming to actually shifting towards writing extremely high quality design docs. So basically, once again, defining the what. And this is actually much more than simple prompt engineering. So high quality design docs, they really require very deep engineering skills because they function sort of as a mental simulation of the system. Um, and as an author, right, you have to anticipate edge cases, navigating also complex architectural trade-offs, and also basically debug this design doc itself. And yeah, I'm wondering a bit, I don't have an answer, but basically what would be the equivalent of a good design doc basically for AC? So maybe, more thoughts need to go into abstractions of representations and also design interfaces. Now, just as a last word, I think also, there are not just similarities, but there are also very significant differences, of course, between software engineering and the AEC sector. So, for example, in software engineering, code becomes more opaque, but it can be very easily updated. And very obviously, we cannot afford to do the same for building processes and build assets. So they are just, to also give you a bit context in the built environment of construction operation of a building. It's, for example, responsible for approximately 40% of the global carbon emissions. And maybe unlike, the energy bill of a house, which you can change by installing some solar panels, the carbon emitted to make the concrete, for example, for a bridge is basically locked in at the moment that this concrete cures, right? And so, yeah, to basically fix this, we have to think, differently probably about design from the very start of creating these structures. So yeah, so probably the ultimate goal is not just do the same with increased efficiency, but rather helping designers to deal with complexity. And again, like this EC perspective, I think we have to design very differently from the start. So basically using different materials, maybe timber, low carbon, green cement, or also think more, for example, about retrofitting of old buildings instead of just knocking things down. Also thinking more about circular construction and allowing reuse. I think this, has of course huge potential for impact on society and how we live. Um, yeah, and just maybe one final word. If you want to go beyond also these optimization-based approaches that I have touched on, basically truly leverage AI system for this, I think it also, we need systems that basically go beyond pixels. So they're basically physically grounded, they can reason in metric space and allow simulation and interaction. And yeah, as a researcher, I'm of course excited about all of these opportunities because it allows us to truly rethink design and design workflows, and with this, of course, also impact the world around us. Yeah, with this, I want to end my talk by actually thanking my wonderful collaborators, students and postdocs that actually have enabled this work, as well as my colleagues. And yeah, I want to thank you very much for your attention, and sorry for going over. Thanks. Thank you for a very nice summary about this work and also for time talk and discussions. And if we have talk, we can have time for our questions. Thank you for this wonderful. I have a very good question, maybe more Um, so basically, I so I mean, in our system so far, basically, you can basically just design, one cell, right, and then basically, tile this. Um, we so in that procedural world, we have not, and I guess it's very interesting future work. I mean, we have not thought, too much about how to basically connect the different cells, right? That you get basically interesting variation. Um, I mean, what you definitely can do, and this is maybe the work I've shown before. So once you basically use the machine learning model there, so there you actually saw quite a bit of variation in the metamaterial structures itself. And there, of course, you have constraints to ensure that they're properly connected. Yes, so there's basically some energy making sure that the boundaries can match. And also, by the way, one very interesting thing to think about is basically, I mean, once you have a cell, right, that is tiled, you can also shift around the basically the representative volume to also try to find better matches. Yeah. Yes. I mean, yes. I mean, usually how we try to operate is basically by trying to collaborate or work with the domain experts. So it's basically in a first step. Yeah, we try to get a bit inspired, right, by basically seeing what are they struggling with, um, and yeah, and then hopefully by giving them these tools, yeah, allowing them basically to yeah be more efficient, right, or maybe discovering solutions that were difficult before, very difficult to do or discover by hand. You could actually maybe almost like Nico would be the better person to answer this. I mean, you have seen when milling it, right? There are like numbers, small numbers milled on it as well. Yeah, you definitely need this, right? Otherwise, there's no chance. But maybe, yeah, Nico, do you want to say something? Yeah. Maybe we need an XR system or something to guide. Yeah. But yeah, maybe in general, actually, not just with this project, but with many other projects as well. Actually, the assembly stage itself often actually gets overlooked, and for example, also just to have the connections properly working, right, was actually huge amount of work. Um, yeah, and I mean now also working a bit with um, architects and people on the construction side. Yeah, basically how to deploy a solution is actually probably, I mean, for many things actually, the biggest hurdle. So there's many things, that are basically nice on the research side, right? But then if you really want to bring it into practice, so that it gets applied, yeah, these are very relevant challenges.
I haven't much about the rectangular concept. So, aesthetics is heavily rely on how compactors version and in others example. So how do you think it's possible to extend it to some form of response information and it's like highly materials? Is it possible to extend it to that or think of some other components?
Uh, I mean, I hope I don't tell nonsense, but basically, I mean, I think extending to nonlinear materials, I mean, if you have the proper basis functions, that should be fine. And I mean, we even had also in our paper, even like some example with nonlinear material models. Yeah, so I, yeah, I think that is not a challenge.
Oh,
Yeah.
thanks.
I- yeah, but I'm also, I have to say, I'm not, the world expert on XFM, so I hope I, yeah.
We don't have options. Sure, right here. Just to chat or doing the great. And here comes to the next is because and it's here again.